Good morning, Year 12 single mathematicians. Just going to quickly go through one of the chapters from the pure textbook that people have requested to revise. It's the chapter called Trig equations or trig identities. It's chapter 10 in the pure textbook. And I'm going to start off with just some basic things you need to know from within this chapter. So first thing is the sketches of the three different trig functions that we've done so far this year. First one being sin x. Sin x has a period of 360 degrees and it starts at 0, it peaks at 1, and the lowest it gets down to is -1. And it looks something like this. Where the highest point is 1, the lowest point is -1, and it takes 360 degrees to complete one cycle of sin x. Okay, another trig function you need to know the shape of the curve for is cos x. Cos x is a slightly delayed version of sin x. Same shape, just starts at a different point. Actually starts at its peak. Looks like this. And again, peak is 1, minimum is -1, and that would be y is equal to cos x. Still takes 360 degrees for it to complete one full cycle, but both of these are trapped between 1 and -1, and that property is needed when asked to solve equations with sin x is equal to a number or cos x is equal to a number which is outside of numbers between 1 and -1. There would be no solutions. Tan x is a little bit different though. Completely different shape. First thing you'll be drawing for tan x is vertical asymptotes, which are points where tan x is undefined. There's no answer for it, and that would be at 90 degrees, and then it would occur every 180 degrees after that, so 270 and so on. And it's a curve which looks like this. It starts at 0, does that, then that is one complete version of tan x, and then that would continue indefinitely. So the one in the middle is just one version of tan x, one complete version, and you can see the length of that period is 180 degrees, so it repeats like this every 180 degrees. That's tan x. Now, in addition to these sketches, you need to know the following diagram. If you look at any other revision for this, it's called a cast diagram. And that just tells you when sin x, cos x, and tan x are positive or negative in the 4 different quadrants. So 0 to 90 degrees is the first quadrant, then 90 to 180 is the second quadrant, 180 to 270 is the third quadrant, and 0 to 270 to 360 is the fourth quadrant, and you could keep going around. Now, in this first quadrant, between 0 and 90 degrees, if you look at every single one of these sketches, whether it's sin x, cos x, or tan x, all of those curves are positive. So we call this A, which stands for all positive. Okay, so all positive. The second quadrant, there's only one of the curves which is positive, and that is sine. In the third quadrant, only one of the curves is positive, the others are negative. That would be tan. And in the fourth quadrant, only cos is positive, the others are negative. We call that C, and then that is abbreviated to A, S, TC, or all stations to Cardiff. You would have come up with your own mnemonic when doing this. That's used to solve equations rather than drawing out the sketches each time. And then the main thing, which is brand new, is some identities. There are two identities you need to know. The first one is called the Pythagorean identity, which is sine squared x plus cos squared x is identical to 1, which means if I picked a random value of x and substituted it into this formula, or this identity, it would always be equal to 1. Problem is with this one, normally you use rearranged versions of this. So that would be the same as if I made sine squared x the subject, I would get this. And if I made cos squared the subject, I would get this. So those two are actually more used than the first one. And the second identity is tan x is identical to sine x over cos x. And again, that would work for every single value of x. Now, these identities, you know, it doesn't have to be an x, it could be a theta. It doesn't have to be just a single theta, it could be 3 thetas. So they can confuse you by using different letters and multiples of letters. But as long as you've got sine squared something plus cos squared of the same something, that's always 1. And same thing for tan. Tan of something is identical to sine of that something divided by cos of that something. And that would be it. Let's see the types of questions they could ask you. E.g. number 1. Given that B is reflex and tan B is equal to root 21 over 2, find the exact value of sine B. Right. When they say exact value like this, that means, or this type of question means you can't use inverse tan or whatever to work out the actual angle itself. There's a way to do this without working out what angle B would be itself. And it is actually relating tan, sine or cos back to GCSE maths and what they would be equal to in terms of socket and toa. So tan is toa, which is the same as opposite over adjacent, which means this angle, or this trig ratio, is connected to a triangle with the opposite being root 21 and the adjacent being 2. So if I just draw a quick sketch of that triangle, it doesn't have to be accurate, call that angle B. The opposite is root 21 and the adjacent is 2. And then using Pythagoras' theorem, you can find out that the hypotenuse would be 5. And the reason why you can work out the hypotenuse, or why you would want to work out the hypotenuse, is because sine is defined as opposite divided by hypotenuse. So sine would be O over H, which in this case is root 21 over 5. Now, the problem with this is because the angle B in this case is a reflex angle, you don't know whether this is a positive root 21 over 5 or a negative root 21 over 5. And the only way to decide is to think about that cast diagram and whether sine is positive or negative in that particular quadrant. So if I very quickly 0, 90, 180, 270, 360, all stations to Cardiff. A reflex angle is between 180 and 360, so it's one of these two quadrants. But also, because they said tan, the original ratio is a positive number, tan is only positive in one of these quadrants. It's only positive in this quadrant. So the quadrant which this angle belongs to is 180 to 270. And in that quadrant, sine is negative. So sine B, the exact value of sine B would be a negative, because it's in the third quadrant. And that would be it for that one. I never used inverse tan or sine or whatever, I just used properties of socket and toa and the cast diagram. Right, let's see a different style of question. So EG number 2, an equation to solve. You got to solve 2 sine 2 theta equals cos 2 theta, where theta is between 0 degrees and 360 degrees. Now when you're asked to solve a trig equation, your main objective is to try and get one trig ratio, a single trig ratio. And this one has 2 of them. So there must be a way to reduce this to a single trig ratio by doing basic mathematical operations. And the only sensible thing to do is think about using those identities on the previous page. So there's no sine squares or cos squares, so it's probably not going to be that Pythagorean identity. However, if I divide both sides by cos 2 theta, what would this simplify to? Well, cos 2 theta divided by itself would be 1, and 2 sine 2 theta divided by cos 2 theta, would be, using that second identity, that would be the same as 2 tan 2 theta. Key thing is tan 2 theta. Now when you've got one trig ratio, you make it the subject. So tan 2 theta would be equal to a half. Now it's very tempting to do a GCSE step now, which would be inverse tan, but there's one thing you have to do before, and that would be work out how many solutions you're going to get, because trig ratios give you can give you multiple solutions, and if you just use inverse tan, you'll find one of them and not the others. So there's 2 things which is wrong with this, which is firstly, I've got a 2 theta rather than a theta, which means my interval needs to be doubled. And then I've got 2 different options to do this. I'm going to draw a sketch actually of the curve and then show you to do this. So I need to go from 0 to 720, and that's 2 theta is what I'm drawing. Tan has some vertical asymptotes, and then tan would be looking something like that, between 0 and 720. Tan goes as high as you want and as low as you want. It doesn't stop at 1 or negative 1. We want it to be a half, which is there. Let's just say it's there. And if you scroll across, you'll see it has 1, 2, 3, 4 solutions. And when we do inverse tan now, it only gives us one of those solutions. So inverse tan of a half gives me 26.6, and that's probably that first solution there. In fact, it definitely is. And the property about tan is the next solution is always 180 degrees more, because tan repeats every 180 degrees. You just add 180 Add another 180. Add another 180. And that would be 2 theta. But you want theta by itself, so the last thing you're going to do is divide each of these answers by 2. So 26.6 divided by 2, we go 13.3 degrees. What would that be? 103.3, so 103 degrees to 3SF. That would be 190, so 193. And this one would be 283 degrees to 3SF for those. And you can always check your answers by substituting them back into the original equation, and they should be right. Right, there's one other style of question you need to be able to do this type. And again, we have an equation with cos squared thetas, cos thetas, and sine squared thetas. And the first thing you've got to do is end up with an equation with one trig ratio only. Got squareds, so you can potentially use that Pythagorean identity, sine squared theta plus cos squared theta is identical to 1. But which one do you choose? Remember, you want the same trig ratio, so the sensible choice is getting rid of sine squared. If I replaced sine squared in equation 1 with 1 minus cos squared, I end up with 1 trig ratio. So substitute 2 into 1 and you get 2 cos squared theta subtract cos theta subtract 1 is equal to 1 subtract cos squared theta. Collect like terms. 3 cos squared theta subtract cos theta subtract 2 is equal to 0. Recognize that this is something called a hidden quadratic. If I replaced every single cos theta with the letter y, for example, you'd get 3y squared subtract y subtract 2 is equal to 0. Solve the hidden quadratic using factorizing or the formula or completing the square, whichever method you do. So that would be minus 1 plus 2, like so, to give you y is equal to negative 2/3 or y is equal to 1. Problem is we didn't want to work out what y was. We want cos theta. You should be able to state the answers to cos theta is equal to 1 without even using a calculator, just via the sketch. Theta is equal to, remember we want between 0 and 360, and cos theta is equal to 1 at 0 degrees or 360 degrees. And then cos theta is equal to negative 2/3. Again, don't try and use inverse cos yet, because you might miss an answer. Either draw a sketch or use the cast diagram. I'm going to use a cast diagram. 0, 90, 180, 270, 360. All stations to Cardiff. Cos is equal to negative 2/3. And in which of these 4 quadrants is cos negative? That one and that one, which means there's going to be an answer in that quadrant and there's going to be an answer in that quadrant. If I start at 0 degrees and I go around to 360 degrees, I've got 2 answers. An inverse cos of minus 2/3 hopefully will give me one of those answers. is 132 degrees to 3SF, which is that first one there, 132. And by the symmetry of the curve and the symmetry of this diagram, that angle there below is 132 degrees. But in order to work out the actual angle I want, it would be 360 subtract 132. So 360 subtract that answer, which gives you 132 degrees or 228 degrees. Those are your values for theta. Now the questions I'd like you to try are actually from the textbook in the review exercise. So the review exercise is on page 229. And I'd like you to try questions 33 to 39. You can just do any of those that look difficult. And if you have any problems, then please rejoin the meeting.